In the previous video, we found out that the probability of the system A having an energy E is a constant C multiplied by number of accessible states for energies in the range E to E plus delta E, and number of accessible states to for the system A prime for energy E star minus E or E prime. Now, I want to recall a few results we had earlier. For example, when we discussed the number of accessible states, we talked about the number of degrees of freedom and quantum numbers that contribute to the total energy. So we said a few things. One thing we said was the contribution to the total energy of the system, E minus E0, where E0 is the ground state energy, was equal to F times the number of degrees of freedom times epsilon minus epsilon 0. So epsilon is the contribution to the total energy of one quantum number in the system, and F was number of degrees of freedom, total number of quantum numbers you have to specify in order to get the state of the system. So epsilon minus epsilon 0 is total energy minus the ground state energy divided by F, the number of degrees of freedom. And the number of accessible states we have for the total energy E was equal to the number of values a quantum number can take for energies less than epsilon, and we have f of those, so we have phi of epsilon multiplied for f factors, total of f factors. So remember, so we would have the number of accessible states phi of epsilon to the power f, where the different values a quantum number can take for energies less than or equal to epsilon is proportional to epsilon minus epsilon 0 to the power alpha, where alpha is of the order of 1. So as the energy increases beyond the ground state energy, we have a more number of values the quantum number can have. So the number of accessible states is then epsilon minus, to a good approximation, epsilon minus, or let's say it goes as epsilon minus epsilon 0 to the power f, where epsilon minus epsilon 0 is equal to E minus E0 divided by f. So the number of accessible states goes as E minus E0 divided by f to the power f. Therefore, you can say that the number of accessible states varies with energy with this function E minus E0 to the power f. So this was an important conclusion we had in our earlier discussion. So that's how the number of accessible states varies with energy E. Now, f is a very large number. F is of the order of Avogadro's number. It's very large, 10 to 23 or so. Therefore, the number of accessible states, omega as a function of E, which goes as E minus E0 to the power f, is a rapidly increasing function of energy. So this is a rapidly increasing function of energy, and at the same time, if you consider omega prime, which is evaluated at energy E star minus E or E prime, this is going to be a rapidly decreasing function of energy. Because I have E star minus E. It's a rapidly increasing function of E prime, rapidly decreasing function of E. So if you consider this product that we obtain here for the probability of the system A having an energy E to E plus delta E, it's proportional to number of accessible states for system A multiplied by number of accessible states for system A prime evaluated at energy E and evaluated at energy E star minus E. So I have the product of two functions. One is rapidly increasing, one is rapidly decreasing with E. So the product, so probability of E, which is C times omega E, omega prime E star minus E, has a sharp maximum because I have a rapidly increasing function multiplied by a rapidly decreasing function. It has a sharp maximum at some energy value I'm going to call E tilde. So you can see here how we envision this. Probability of the system A having an energy E has a very sharp maximum at E tilde with a width of the this peak being delta E. Okay, so what is the meaning of having a sharp maximum? So we say that the maximum or the point at which the maximum occurs we called E tilde, the energy value E tilde. So this is going to imply that at this point del P del E is equal to 0, right? So it has a maximum, and the width of this peak delta E is much less than E tilde. It's a very sharp peak. All right. And on the other hand, if you consider a natural logarithm of the probability of E, you will have natural logarithm of C, natural logarithm of omega plus natural logarithm of omega prime. Now, since the number of accessible states omega and omega prime are varying rapidly with energy, the natural logarithm is somewhat has a somewhat slower dependence on energy E. So if you look at natural logarithm of omega, natural logarithm of omega prime, and if you add them up, you get this white curve, and this has a maximum also at this E tilde value. All right, so therefore if I look at, instead of the probability as a function of E, I can consider the derivative of the natural logarithm of the probability with respect to energy E, and this is 1 over P del E. Del P del E was 0 at E tilde, so this is going to be equal to, when E is equal to E tilde, this will be 0. All right? It's because it's the maximum. It's the maximum of probability function, it's the maximum of natural logarithm of the probability function as well. So if I look at the natural logarithm of the probability here, this is going to, so let's take the derivative. A natural logarithm of C with respect to E plus the natural logarithm of omega E with respect to E plus the natural logarithm of omega prime E star minus E with respect to E. This has to be equal to 0. Now we have here E prime. E prime was basically, remember, the energy of the prime system A prime. So we have here E prime So basically what I would like to know is what is the derivative of natural logarithm of omega prime at E star minus E with respect to E. So if I can find by considering E prime, so E prime is E star minus E. So if you consider dE prime, this is going to be equal to minus dE because E star is a constant. So this is going to tell me how this derivative can be turned into an E prime derivative. So the first term here, a constant derivative with respect to energy, this is going to be 0. So I will have the derivative of natural logarithm of omega with respect to E minus the natural logarithm of omega prime at E prime with respect to E prime, because I have made this substitution. dE prime is minus dE, so for delta E this is going to become minus delta E prime, and I substitute E prime is E star minus E. This has to be equal to 0 at E is equal to E tilde. So I'm going to define this derivative as beta. Beta parameter is a function of energy, is defined as del ln omega del E, which is 1 over omega del omega derivative of accessible states with respect to energy. With this definition, I get beta at energy E is equal to beta prime at energy E prime at E is equal to E tilde. Del ln omega del E is equal to del ln omega prime del E prime. Okay, so this is the conclusion for the maximum probability condition. I have betas of those two systems should be equal. Now you can see that beta is a derivative of number of natural logarithm of accessible states with respect to energy. So what is dimension of beta? With this definition I find that dimension of beta is 1 over energy, and I'm going to call therefore 1 over beta some energy. I'm going to define this as kT and call this thermal energy kT, and T is called absolute temperature, and K is a constant, it's Boltzmann constant. So this basically defines the absolute temperature. So we have the relationship between absolute temperature and number of accessible states. Now I'm going to take the definition of beta. Beta is equal to 1 over kT, or defined as 1 over kT, which is del ln omega del E. So you can see that 1 over T is equal to del K ln omega, Boltzmann constant, times natural logarithm of accessible number of accessible states del E, and I'm going to define S as K ln omega. So this is S is K ln omega. So with the number of accessible states is a parameter states variable of the system that increases with the number of accessible states. So here S is called the entropy of the system. Well, since I'm using omega, it's the entropy of the A system, not A prime. Okay, the number of accessible states is just a number. There is no dimension to it. The dimension of S is energy due to Boltzmann constant K, which has energy dimension. Okay, and what is the meaning, physical meaning of S? Because it's counting the number of accessible states corresponding to a particular state. S gives a quantitative measure of the degree of randomness. Quantitative measure of the degree of randomness. So it's an important parameter. Now I want to know what happens to S when I'm at equilibrium. So when I reach the maximum possible probability at E is equal to E tilde, I have del ln P del E equals to 0. So it's del ln omega del E minus del ln omega prime del E prime is equal to 0. If you multiply this equation with K, you will find that the condition you have is del K ln omega del E minus del K ln omega prime del E prime is equal to 0. So this is basically K times beta minus K times beta prime is equal to 0. So K 1 over KT minus K 1 over KT prime equals to 0. In other words, the absolute temperatures must be the same. So the condition for which we're going to have the maximum probability of having an energy E tilde for the system A will correspond to the condition where the temperatures are the same. And if I look at the left hand side of this equation, so this is K del ln P del E, so that was the left hand side. At E is equal to E tilde, K ln P derivative with respect to E is 0. It's a maximum. So we have K ln C plus K ln omega E plus K ln omega prime E prime. This is a maximum at this point. All right. So therefore, if you consider what is happening in terms of entropy, so K ln omega is entropy of system A, K ln omega prime is entropy of system A prime, and the total is a star, total entropy. This has to be a maximum. So basically another condition for the equilibrium situation, maximum probability, it corresponds to the maximum entropy of the total system. So for the total system A star, the isolated system, to be distributed over the largest possible number of states, That is to say, it is in the most random macro state, random or disordered macro state. The total entropy S star, which is k ln omega star at this energy E, must be as large as possible. Now, one more thing I would like you to notice here is the following. The entropy, which is k ln omega for system A, this is at energy E. So if you take the derivative of entropy with respect to energy, so it is ds dE, you're going to get k del ln omega del E, and this is basically the beta parameter we have here. So it is k times beta, so this is 1 over the temperature. So I find that ds, a small change in the entropy, is dE divided by T, and I also know that dE bar is equal to d bar Q for thermal interaction, since I have W is equal to 0 and d bar W is equal to 0 for thermal interaction. So I find that change in entropy is d bar Q divided by the absolute temperature T. So for a quasi-static process, infinitesimal change in entropy is related to the infinitesimal amount of heat added, d bar Q, at constant absolute temperature T. Okay, so let's summarize what we said here. First of all, we started out by saying the total energy of system A, E minus E0, the ground state energy, is number of degrees of freedom, total number of quantum numbers you have to specify to get the state of the system, multiplied by the energy contribution from each quantum number, epsilon minus epsilon 0. So epsilon minus epsilon 0 is total energy minus total ground state energy divided by F. And the number of accessible states at this energy was equal to the number of values each quantum number can have for energies less than epsilon. And this is going to be done f times, so it is phi to the power f, and the number of values a quantum number can take depends on its energy. If the energy is the lowest possible energy, there is only one quantum number value. As the energy increases beyond the ground state energy contribution epsilon 0, the values it can take increases accordingly, and more or less linearly. So we have the number of accessible states is proportional to epsilon minus epsilon 0, the contribution to energy from each quantum number, to the power f, number of degrees of freedom. And because epsilon minus epsilon 0 is E minus E0 divided by f, the number of accessible states varies with energy according to E minus E0 to the power f, where f is the number of values you have to specify, number of quantum numbers you have to specify in order to get the state. So for a macroscopic system, this is very large, of the order of Avogadro's number. So the number of accessible states varies rapidly with energy. So it increases rapidly. So for omega prime, the primed system with which we have thermal interaction, whose number of accessible states are evaluated at energy E star minus E to E star minus E plus delta E, where delta E was very small so that the number of accessible states is not changing. This is a rapidly decreasing function of energy E. because it's E star minus E. So it's a rapidly increasing function of E prime. It's a rapidly decreasing function of E. So the probability of system A having an energy E to E plus delta E, we have found in our previous discussion to be a constant times number of accessible states to system A for energies in the range E to E plus delta E, with the number of accessible states to system A prime with energies in the range E star minus E plus delta E. So the product of two functions, one is rapidly increasing with energy, one is rapidly decreasing with energy, gives you a very sharp maximum at a certain point E tilde with a very small width delta E. It's a sharp peak. So we have decided, instead of looking at this probability function, if we look at its natural logarithm, we will be dealing with a much slower variation with energy E, so that the summation of ln omega and ln omega prime will give me a nice function which has a well-defined maximum that I can find easily. So for a smooth slow variation with energy E, we have decided to work with natural logarithm instead of the function itself. Alright, and at the maximum point, for maximum probability, we need to have dp de equals to 0 or del ln p del e equals to 0. So you can see it's the same maximum point here we see for the sharp peak and for the natural logarithm ln omega plus ln omega prime. It has the same peak at this location. So that the derivative has to be equal to 0. If you consider the right hand side, del ln c del e, a constant derivative with respect to energy, is 0, and then we have del ln omega del e plus del ln omega prime at e star minus e del e. Now e star minus e is e prime, the energy of the prime system, and de prime is minus de. So we can see here that for the maximum probability, we must have del ln omega del e equals to del ln omega prime del e prime. And we have defined beta to be del ln omega del e, whose dimension is 1 over energy, because we have a number divided by energy, a change in energy here, delta E, so it's 1 over energy. 1 over beta has the dimension of energy, it's called thermal energy, and we define it to be kT, where T is absolute temperature, K is Boltzmann constant. And if you multiply ln omega with K, so if you consider 1 over kT equals del ln omega del E, you will see that 1 over T equals del K ln omega del E, and K ln omega is a state variable, so it's proportional to natural logarithm of number of accessible states in the system. It's called the entropy of the system. It's a quantitative measure of degree of randomness. The more accessible states we have, the higher the entropy, and its dimension is given by K, which has an energy dimension. So when E is equal to E tilde, the maximum probability point, we have this equation del ln p del e equals to 0, and looking at this equation I realized that the maximum point corresponds to beta equals beta prime, or temperature T, absolute temperature T on the unprimed system equals to temperature T prime of the primed system. So equilibrium corresponds to the same absolute temperatures. And at the same time, since del K ln P del E is equal to 0, that means we're looking at the maximum of K ln P function. So it is K ln C plus K ln omega plus K ln omega prime. This is a maximum at this specific point E tilde. K ln omega is entropy of system A, K ln omega prime is entropy of system A prime. So the total entropy, a star, must be a maximum at this point. And this basically implies for A star to be distributed over the largest possible number of state, i.e. it's in the most random macro state, most disordered state, the total entropy S star, which is K ln omega star at this energy E, must be as large as possible. And if you go back to S is equal to K ln omega, this is definition of entropy here. Take the derivative of S with respect to energy E. You have K del ln omega del E. It's K times beta, which is 1 over T. So ds is equal to dE divided by absolute temperature T. Now what is dE bar? If it is a thermal interaction which doesn't have any work or small amount of work done on the system, you have dE bar is equal to d bar q. So as an infinitesimal change in entropy is infinitesimal amount of heat added divided by temperature T.